Our next presentation is about gemstones and photoluminescence. It will be presented to us by Dr. Claudio Milisenda, Managing Director from the German Gem Laboratory. Claudio?
Thank you, Shane. Good morning, ladies and gentlemen. Yesterday, we heard about the use of photoluminescence techniques in order to identify synthetic diamonds. I'd like to give you some examples on how this can be applied to colored stones. Now, the observation of the luminescence has also always been and still is a very important criteria when it comes to the description of gemstones. And whenever there are articles on new gemstones or gemstones from new deposits, it is described how these stones behave under ultraviolet light. And you find of whether the fluorescence or the phosphorescence is more significant under shortwave UV and longwave UV, how is the color, and so on and so forth. Now, it was then starting from the 1980s that people start to look at the luminescence at magnification. So to look how is the luminescence distributed within a stone. And this was actually one of the first who introduced the luminescence excited by electrons from cathode ray was the late Johann Ponalo from Austria. And he used, as I mentioned, the luminescence to visualize growth patterns. And this is actually one of his slides that he published in the late 1980s in our journal that made visible the typical cubo-octahedral growth that help you to identify HPHT-grown synthetic diamonds. Actually, the first publications that he made on cathodoluminescence was to distinguish between natural and synthetic ruby and natural and synthetic emeralds. At that time, gemologists did not pay much attention to that because the machine was actually too expensive. Nobody had a cathodoluminescence in the laboratory, and at that time there were other methods available with which you can distinguish between natural and synthetic ruby. Then in the mid-1990s, De Beers introduced the diamond view, where you can actually produce the same luminescence pattern by exciting a diamond with strong shortwave UV. And you can see actually the same pattern. And since these devices are on the market, increasing studies on photoluminescence have been published predominantly on diamonds, not so much on colored stones. You can also induce in some type of synthetic diamonds the photoluminescence by other wavelengths. This is conventional shortwave UV, 254 nanometers, and sometimes you can even identify the synthetic diamonds with a 405 nanometer laser pointer. So, in addition to the imaging of luminescence, the spectroscopy of luminescence became more and more important, particularly since the appearance of HPHT-treated diamonds. And the photoluminescence spectroscopy is one of the most sensitive optical methods with which you can detect emitting centers which are otherwise not possible to identify by other methods. And colored stone application. And some examples that have been published was the separation of natural and synthetic spinel, identification for heat treatment in spinel. These were own experiments that we made. There were also some other publications available in the literature on that phenomenon. This is the chromium luminescence spectrum of an untreated spinel, and with increasing temperature, these luminescence band broaden, and the maximum of the luminescence, or the maxima of the luminescence band, is also shifted towards longer wavelength. So that's actually the only method with which you can identify the heat treatment of spinel. Other applications were the detection of dyeing of corundum, and also the dyeing of corals and pearls, because organic pigments are also important luminescence centers. That's another application. Fracture filling, and also the origin determination of corundum, at least in the indication of the origin determination of corundum, because the chromium luminescence in corundum is quenched by iron. And not only the intensity is decreased, but also the luminescence bands are shifted towards lower wavelength, the higher the iron concentration. And you can calculate actually from the shift the concentration of the iron in the corundum. This helps you, for example, to separate between a metamorphic and a basaltic type sapphire. Now, we recently had a closer look at the photoluminescence in Alexandrite. Alexandrite is orthorhombic and crystallizes in the olivine structure, and important is that there are actually two non-equivalent octahedral sites in which aluminium can sit in the structure. One is called the inversion site. The inversion site, the aluminum sits in an inversion center, and then there is IL2, which is in the mirror side, where the aluminium sits in a mirror plane. And this is quite important because so the local symmetry in these octahedral sites is different. To produce Alexandrite, aluminum has to be replaced by chromium. So chromium can also be in two different positions in the crystal lattice of chrysoberyl, and therefore you have two different luminescence centers. Now, if you now look at a photoluminescence spectrum of Alexandrite, and we look first of all at the synthetic Alexandrite, and I choose this because this is a sample which is chemically relatively clean. So in addition to beryllium and aluminum, it's only very little chromium, 0.59 weight percent, very low iron, so the quenching, iron is a quencher of luminescence, is very low, and there is no vanadium. And then you can see here two bands. First of all, R1, R2, which is a result of the chromium in the Al2 side, and S1, S2, which is a result of chromium replacing aluminum in the Al1 side. This is excited by 540 nanometer laser, and now I'm comparing this with one type of natural Alexandrite, this one here. This has chromium 1.14%, iron 1.91%. You see that the S1, S2 bands are actually entirely lacking. But there are also natural Alexandrites where the iron concentration is low. So there can be some S1, S2 bands, and there are also chromium, there are also synthetic Alexandrite like this one here with higher iron concentrations where the S1, S2 bands are very low. So at first sight, it appears that you can have very similar luminescence spectrum in natural and in synthetic Alexandrites. But again, if you compare them under the same measurement conditions, so same wavelengths, same energy of the laser, same intensity, same accumulation times, you can see differences. Here, you can see a number of luminescence spectra of natural Alexandrites from all known deposits: Sri Lanka, Brazil, Russia, Tanzania, India. This, by the way, is a natural Alexandrite from the hematita deposit in Brazil with a weight well above 20 carats, and it's almost eye clean. But that's an extremely rare natural Alexandrite. Now you can see here that the spectrum is very, very noisy, and if you now compare it with synthetic Alexandrites, you can see that in synthetics, the spectra is much, much smoother. The intensity of the bands is also higher. Again, at same measurement conditions. That is quite important to point out. Now, what is the use of that? sometimes you have stones which do not fit in your instrument. You can, for example, easily distinguish between natural and synthetic Alexandrite with infrared spectroscopy. But if you have a stone like this did not fit in our infrared spectra, or you have stones, large, rough stones, stones which are mounted, or stones which are in a museum, so the stone does not come to your laboratory, you have to go to the stone, then it is quite useful to use some of these synthetic diamond the diamond devices that we heard about yesterday. So instruments, portable instruments that are actually constructed to separate natural from synthetic diamonds, and there are plenty of those available. And if they are working, many of them are based or have the working principle of photoluminescence. And so we used one of these. That's the one produced by Margilam's EXA. The advantage of this is that you not only have a pass and a refer thing, you have a probe with which you can illuminate, excite the sample, and then you can also observe, you can measure the spectrum. And we did that here. Now, first of all, the general spectra told us that we are dealing with a chrysoberyl. So you can, with photoluminescence spectra, providing that you have a reference spectra, identify the mineral species. And the pronounced S1, S2 bands also strongly suggest that this is a synthetic Alexandrite. So the whole thing here was a fake. So that is synthetic Alexandrite glued into a piece of rock. The same you can use for identifying dyed corundum. This is a piece of dyed corundum under UV light. You can see here the strong orange fluorescence in the fracture, and in the luminescence spectrum you can see here in the dyed part the orange luminescence band. So you can use this for screening. So for example, you have a lot of ruby caps, and you can just go analyze the stone one by another. First of all, you can see that it is a ruby, and secondly, you can see whether it's dyed or not. You know that Cuprian tourmalines were first found in the Paraíba state in Brazil, and they are known as Paraíba tourmalines in the trade. But today, most of the Cuprian tourmalines actually are from Mozambique. They were first found in the Mavuco deposit in Mozambique. This is a typical range of colors that you find there, untreated stones, and they were actually identified as copper manganese variety of elbite tourmalines. Now, since about 2 or 3 years, we saw an increasing amount of stones which showed a distinct greenish, yellowish greenish fluorescence under long wave UV. So this is the type material we are looking at. This is how they appear in the rough, untreated form, and they are commonly heated to produce this nice turquoise blue colors. And they are not from the Mavuco deposit, they are from a deposit called Maraca, which is some 25 kilometers away. And they are chemically different. We have learned about the tourmaline structure and chemical composition earlier this morning. And these tourmalines from Maraca are, compared to the stones from Mavuco in Mozambique and compared to those from Nigeria and Brazil, chemically different. They plot here in this tiny diagram in the calcic group, and they can also be identified actually as liddicoatite tourmalines, so calcium-rich tourmalines. Now, calcium-rich tourmalines or calcium-rich minerals commonly also contain rare earth elements, and rare earth elements are very important luminescence centers. And so we actually analyzed these stones. This is a photoluminescence spectrum excited by a 785 nanometer laser. And you can see here, in addition to the Raman spectra, additional bands which actually are photoluminescence bands. In the next slide, we analyzed the same stone at liquid nitrogen temperature, and we fitted the curve, and it produced actually, I think, 15 individual luminescence bands which could be attributed to the rare earth element neodymium. So chemical analysis produced by laser ICP-MS analysis showed actually elevated concentrations of the rare earth elements, particularly the light rare earth elements in the Maraca deposit, whereas in the Mavuco deposit, in the Elbaites, rare earth elements were actually absent. So if you measure the luminescence spectrum of a tourmaline, of a Cuprian tourmaline, and you can identify that they are enriched in rare earth, you can tell that they are from Mozambique, from that particular deposit, because until now we haven't seen any rare earth-bearing tourmalines, Cuprian tourmalines, in the other deposits. This here, these are all stones that have been submitted to the laboratory, to our laboratory. The one in the middle showed a different rare earth spectrum. This is apatite. It has been submitted as Cuprian tourmaline, as Paraiba type tourmaline. These are tourmalines. This is an apatite. You can see also a rare earth spectrum. The bands, however, are at slightly different positions. This is logical because apatite crystallizes in the hexagonal crystal system. So this means that the geometry around the luminous center is different because the mineral has a different crystal structure. This small stone here was also submitted together with Cuprian tourmalines. That's a tsabolite. And tsabolite is also known to contain abundant rare earth, and this is the rare earth-induced photoluminescence spectrum of tsabolite garnet. And we compared it with a hessonite garnet, and the hessonite garnet shows actually virtually the same rare earth spectrum. This is logical because they are both crossular garnets having the same crystal structure. And this is one of these color change classes, rare earth induced color change classes that you can typically buy in Turkey as sultanite imitation, which is often sold to the tourists. This particular necklace was purchased for $20,000 in Turkey. So these bands here are also a result of rare earth luminescence, but glass is an amorphous substance. That means that the bands actually are much, much broader compared to the rare earth bands in crystalline substances. Yeah, to summarize this, there is a great potential of luminescence techniques for colored stone applications. The spectra, similar to Raman spectra, can be used for the identification of gemstones, providing that you have reference spectra, of course. They can also be used as an additional indication of a gemstone's origin, as has been demonstrated for the Mozambique Cuprian tourmalines. And there's also potential for screening devices. So yesterday, as I showed you for the natural synthetic Alexandrite and also for the dyed ruby, yesterday we saw a slide with all these various devices which now are offered to identify or to separate natural from synthetic diamonds. And I want to encourage the producers to modify their instrument so that you can switch from a diamond mode into a colored stone mode. And then I would buy such an instrument. Thank you very much for your attention.
Okay, thank you very much, Claudio. We have time for a couple of questions.
There's one over there.
Hi, yes.
Thank you very much. Is photoluminescence of value in differentiating oil from resin in fracture-filled emerald?
It is, yes. Yeah.
In the back.
Can you just clarify, were you using conventional ultraviolet light for all of those?
That device, that portable device, uses strong long-wave ultraviolet light. So that's stronger than the 366 that you normally use. It's about 330 nanometers. And the others that I showed you, these are laser-induced with the Raman spectrometer. 785 for the rare earth, 515 for the chromioluminescence in Alexandrite. But I mean, you can also use other lasers.
Well, I was wondering if you've tried visible wavelengths across the filter.
No, we didn't so far.
If we don't,
For the chromioluminescence, the visible light is not enough to make visible the bands to separate between natural and synthetic Alexandrite. No, you need the ultraviolet light source, ultraviolet light source.
I'm just suggesting that with LED technology, you can get a bright blue, even a copper laser.
Sorry, I cannot understand you very well. Can you?
Speak a bit louder. I'm just suggesting that the pocket lasers that are blue and green would be enough to kick in.
Yes, but for the separation between natural and synthetic Alexandrite, we have to observe the spectrum. We have to measure the spectrum. It's not just an imaging thing; it is spectroscopy.
Okay, thank you very much. We'll have to move on. Thank you very much, Claudio.